Imagine a world where your online gaming session lags out at the critical moment, costing you the win. Or maybe worse, where a company's entire cloud infrastructure just grinds to a halt, costing millions in lost revenue and, damaged reputation. What if I told you that these kinds of digital disasters, they aren't random acts of tech fate. Often they're actually preventable failures in network performance and recovery. From the cloud to your coffee maker, everything is connected, and it all starts with data communications. Welcome to the Deep Dive. Today, we're pulling back the curtain on the critical world of network performance and recovery. This isn't just about, understanding wires and Wi-Fi. It's really about the strategic backbone of every single modern organization. For anyone forging a career path in information systems, computer networking, cybersecurity, well, mastering these concepts isn't just academic. It's like having a superpower for career success.
That's absolutely right. Our mission today is really to equip you with the knowledge, the insights to understand not just how to design and build high-performing, resilient networks, but also how to anticipate, respond to, and, importantly, recover from the inevitable challenges that come with our hyper-connected world. We'll cover everything from, monitoring the heartbeat of your network all the way to formulating robust recovery plans, skills that will truly position you as an invaluable asset in any organization.
Absolutely. Couldn't agree more. And as we embark on this crucial deep dive, please take just a moment to like, subscribe, and share. Your engagement really helps us bring more insider tips and knowledge your way, positioning you for career success. And remember, you'll find additional resources to expand your learning down in the description below. Okay, so let's unpack this journey. Let's start at the very foundation, collecting network data. This is where network management truly shines, doesn't it? I think a lot of people might think network management is just about making sure the internet works, but it's a far more multifaceted discipline, right? What's the real scope we're talking about here?
Yeah, it's definitely much broader than just keeping the lights on, so to speak. Network management encompasses, well, everything from meticulously controlling user access to resources to constantly checking for hardware faults that could lead to those cascading failures, ensuring that critical applications, maybe like a company's sales system, always get the quality of service, the QoS they need. It also involves maintaining comprehensive records of all your network assets, software configurations, and even determining the optimal time for upgrades to avoid disrupting operations. It's a big job.
Okay, so if that's the scope, what's the underlying strategic goal? I mean, beyond just keeping things running, what are administrators really trying to achieve?
Well, the core objective across all these different facets is always pretty much the same. Enhance efficiency, boost performance, and prevent those costly downtimes or data losses that can, frankly, cripple a business. But here's the key insight, I think. Ideally, effective network management helps administrators predict problems before they occur. It fundamentally shifts you from a reactive stance, always putting out fires, to a truly proactive, preventative approach, this predictive capability. It's a cornerstone of modern information systems management. It empowers you to design, integrate, and implement communication solutions that aren't just functional, but genuinely resilient.
And, before we even touch a keyboard or think about software, we have to consider the physical environment. This is where it gets really interesting, because no amount of digital security or software wizardry can compensate if your physical infrastructure is, well, literally crumbling around your critical equipment. We're talking about environmental monitoring, essentially, checking the vital signs of your network's physical home. What are some of those silent dangers lurking in a server room if you're not paying attention?
Exactly. You have to think of a data center not just as racks of servers, but as a carefully controlled ecosystem. If you ignore its climate, you're basically asking for trouble. Key factors like temperature and humidity, whether it's for individual devices, entire racks, or the whole room, they're paramount. Uncontrolled conditions, too hot, too cold, too damp, they can silently chip away at hardware lifespan and severely impact performance, leading to unexpected and very frustrating failures that just seem to come out of nowhere.
Oh, I can imagine the frustration. Totally. And it goes beyond just climate control, right? What about more overt physical threats?
Absolutely. We're talking about the physical integrity and safety of the environment itself. Are there liquid detectors to warn of flooding? Smoke or fire sensors that can trigger an immediate response? Is there adequate airflow? That's crucial for cooling and preventing overheating. Even physical security aspects are critical. Motion detectors, security cameras, knowing if room lights are on or off unexpectedly, or if room or rack doors are open when they shouldn't be. These are all indicators of potential security breaches, unauthorized access, or maybe even just a careless technician.
And you absolutely can't overlook the lifeblood of all our electronics.
Power stability. I've heard horror stories of networks brought down by something as simple as like a flickering light.
That's spot on. Monitoring voltage, battery levels, power outages, power consumption, it's all vital. Even minor fluctuations, things like power surges, those sudden spikes or brownouts, those momentary drops in voltage, they can cause serious cumulative damage to sensitive computer equipment. And they're often a really frustrating, hard to pinpoint source of intermittent network problems that leave administrators scratching their heads.
So picture this. Imagine a data center just blanketed with this network of tiny, vigilant sensors, all constantly feeding environmental data into a central network monitor. This isn't just passively collecting data, it's actively creating alerts and notifications the moment a predefined threshold is breached. For you, as future business leaders or IT professionals, understanding these physical vulnerabilities is absolutely paramount. It's crucial for formulating accurate risk assessments and designing truly robust network infrastructure. Infrastructure that can withstand more than just digital threats. Ignoring the physical layer is like building a skyscraper on a foundation of sand. Just won't work. Okay, let's zoom in now. From the physical environment to the very digital pulse of the network. Let's talk traffic monitoring tools. These aren't just gadgets. They're specialized windows providing a really deep, granular look into every conversation happening on your network. Some of them are fantastic for real-time analysis, giving you immediate alerts, right?
Yeah, instant feedback.
While others are designed more to log data for later, retrospective analysis. Like digital forensic investigators meticulously piecing together a complex puzzle.
Right. Fundamentally, a network monitor is a comprehensive software or hardware solution. It allows administrators to observe, capture, analyze, and manage network traffic and device performance. To really understand how many of these work, you need a little technical insight. The network adapter, the NIC, in the machine running the monitoring software often needs to support something called promiscuous mode.
Promiscuous mode. Okay, that sounds intriguing. Can you break that down a bit more simply for us?
Sure. Think of your network card like a postal worker. Normally, it only accepts mail specifically addressed to your house, your computer. In promiscuous mode, it's like that postal worker suddenly decides to open every piece of mail passing by on the street, regardless of the address, and takes a copy of it for analysis. This allows the NIC to capture all traffic on a network segment, not just the packets specifically addressed to it. It's an incredibly powerful feature for deep monitoring, giving you an unparalleled view of network activity.
That's a fantastic analogy, okay. So these tools capture raw network data, individual frames, and can even reproduce past network conditions for forensic analysis.
Yeah.
Wow. They're churning out vital statistics about traffic volume, protocol usage, error rates, but some go even further with advanced functions, like node discovery, automatically identifying all connected devices, building an inventory, creating visual network maps. That's huge.
Yeah, it saves a ton of manual work.
And these systems establish baselines of normal behavior, track utilization, store data for reports, trigger alarms based on thresholds, detect anomalies. It's really a foundational understanding of how network architecture supports troubleshooting techniques. That's a critical skill, a key knowledge outcome for any aspiring IT professional.
And when we talk about abnormal data patterns, we're really talking about the network's own distress signals. It's a way of screaming for help, basically. Recognizing these is critical for rapid troubleshooting. For example, imagine a user complaining their critical business app is constantly freezing or dropping data. One of the first things an admin might look for are runts, which are Ethernet frames smaller than the minimum 64 bytes, or giants, frames larger than the max 15-18 bytes. These often point to a malfunctioning network card or maybe a duplex mismatch, causing those intermittent issues. Then there's Jabber.
Jabber.
Yeah, it's a continuous stream of random, meaningless data transmitted by a device. It's a classic telltale sign of a faulty NIC that's just gone rogue.
So like a device just shouting nonsense on the network, making it hard for other devices to communicate properly?
Exactly that. And even more frustrating sometimes are ghosts. These are corrupted signals or packets that appear and disappear intermittently. They're notoriously hard to diagnose because they're so elusive. And of course, packet loss and discarded packets directly indicate congestion, hardware issues, or even configuration problems. While interface resets, a network card or port constantly restarting itself can cause really frustrating traffic interruptions. Recognizing these specific abnormalities helps IT pros quickly pinpoint and address underlying network problems. It's crucial for maintaining optimal performance. It's truly a masterclass in applying appropriate network troubleshooting techniques for any given scenario. It's a key skill.
Okay, so beyond live traffic, we also have system event logs. These are like the network's historical record, sort of a black box for every action.
Oh.
On Windows, you have the event log, easily viewed with the native event viewer application, right?
Mm-hmm.
Virtually every condition the OS recognizes gets recorded there.
And for Unix and Linux systems, you have syslog. This is a standardized protocol for event message format transmission handling across those systems. It defines two primary roles: a generator that creates the log messages and a collector server that receives and stores them. Syslog even includes 9 severity levels, from emergency all the way down to debug, to categorize the urgency of events. The challenge, though, is that while it's incredibly comprehensive, managing and extracting actionable insights from massive syslog files requires thoughtful data filtering and sorting. Otherwise, you're just drowning in information overload, like trying to find a needle in a digital haystack.
Yeah, information overload is a real problem. So how do we tie all this data collection into a larger, coherent system? What's the architecture that brings it all together?
That brings us nicely to the network management architecture. At the heart of it all is the NMS, or Network Management System, server. This is the central hub where your monitoring software lives. It collects, analyzes, presents data from all your managed devices. And managed devices can be anything: routers, switches, servers, firewalls, printers, anything on your network that can be monitored remotely. On each of those managed devices, you have a network management agent. That's a piece of software that collects specific local management information and sends it back to the NMS. This information is stored in a MIB, or Management Information Base, which is essentially a virtual database residing on each device, containing a hierarchical collection of variables representing its status and statistics.
And this is where SNMP, Simple Network Management Protocol, comes into play, right? I've heard it called the universal language of network devices.
It is indeed the de facto standard for monitoring network devices. Agents use SNMP to populate those MIBs and communicate status information back to the NMS. But there's a huge caveat here, and this is absolutely crucial for anyone involved in network security. SNMP v3 is the only version considered secure due to its robust authentication and encryption capabilities. Older versions, especially SNMP v1, have significant security vulnerabilities. They should absolutely be avoided in modern networks, if at all possible. Using them is like leaving your network's front door wide open.
Wow. Okay, so if you're stuck with older devices or legacy systems, and you absolutely must use older SNMP versions, what are the bare minimum security measures you need to put in place?
Yeah, good question. If it's truly unavoidable, you need to implement stringent security measures. Disable SNMP entirely when it's not strictly needed. Limit approved sources to specific NMS IP addresses. Require read-only mode to prevent configuration changes via SNMP, that's a big one. And use strong, complex community streams, which are essentially passwords, making sure to use different ones for various device groups. These are crucial steps to configure network connections and security for any given set of requirements. You can't skip these.
What's fascinating here is how the SNMP manager, which is part of your network monitoring system, actively sends out broadcast requests to discover devices. Device agents then respond by sending their MIBs, allowing the manager to automatically build a complete hardware inventory and even generate a network topology map showing how everything connects. It's like the manager taking a complete census of your digital neighborhood. It's pretty neat.
And this is where the SNMP trap becomes truly invaluable. See, a device agent doesn't have to wait for a request if it discovers a problem. Like, say, a critical resource threshold being exceeded. Maybe a server CPU usage spikes dangerously high. It immediately sends an SNMP trap to the manager, which the network monitor then interprets into an alert. This completely automates network monitoring, ensuring technicians only need to intervene when a problem arises, rather than constantly polling devices just for status updates. It's a proactive early warning system.
That's efficient. So with all these capabilities, what kind of tools are out there helping administrators leverage SNMP and other protocols? There must be a wide array of options available.
Oh, absolutely. The landscape of network monitoring tools is rich and varied. Instead of trying to list every single one, maybe let's highlight a couple of distinct approaches just to give a flavor. For example, you have tools like H.Schuessler PRTG Network Monitor. It offers a really versatile solution using SNMP, packet sniffing, WMI, providing extensive sensors for everything from bandwidth to hardware health. It's highly customizable, offering dashboards and threshold-based alerts that can notify you via email, push, even Slack. It's a comprehensive platform for keeping tabs on diverse network elements.
Okay. And what about for organizations with multiple sites or maybe managed service providers? Are there tools tailored for those kinds of needs?
Definitely. Take Avik as an example. It's a SaaS solution, so cloud-based. known for quick deployment and automated network mapping. That makes it ideal for managed service providers, MSPs, and multi-site businesses. It centralizes management and provides automated resource utilization alerts and configuration management, essentially giving you a single pane of glass view across many disparate networks, so you have solutions that range from deep on-premise monitoring to expansive cloud-based management for complex environments. These tools help in selecting appropriate networking components and configuring efficient network management. And frankly, knowing these tools exist helps prepare students for those industry standard network certification exams too.
So we've talked a lot about individual device health with SNMP, but what about understanding network communications as a whole? That bigger picture, that's where NetFlow comes in, right?
Exactly.
It's a monitoring protocol, originally from Cisco, that tracks all IP traffic crossing an interface where it's enabled.
Yeah, and the key distinction here, and it's a critical one for effective network management, is that NetFlow focuses on network communications as a whole, identifying top talkers, application usage, traffic patterns across the entire network. SNMP, by contrast, focuses on individual device health and performance. With NetFlow, devices generate flow records. These are summaries of traffic flows, not the full packets.
Oh, okay.
And they send them to a NetFlow collector. A NetFlow analyzer then collates these records to provide deep, actionable insights into traffic patterns, helping you understand who is talking to whom, what they're talking about, and how much data is flowing between them.
That's a really great clarification. Thanks. So for our learners, this raises an important question. When would you use SNMP, and when would NetFlow be more appropriate in a business scenario? Can you give us a real-world example?
Sure. Let's use an analogy. Imagine your network is a large apartment building. You'd use SNMP if you want to know if specific appliances in each apartment are working. Is the fridge on? Is the water heater functional? It's about checking the health of individual devices and getting alerts if a specific one breaks. You'd use NetFlow if you want to understand the overall activity of the entire building. Which apartments are using the most water? Which are leaving their lights on all night? Or, maybe more critically, if there's an unusual amount of traffic going to a specific outside address, which could indicate a problem. So NetFlow is for high-level traffic analysis, capacity planning, identifying those bandwidth hogs, or detecting unusual, potentially malicious traffic patterns across your entire network. Both are crucial, but they answer different questions about your network's behavior.
Okay, so as our networks increasingly extend beyond our own four walls out into the cloud, a new kind of evolving concept emerges. Cloud observability. Cloud service providers, CSPs, offer tons of services designed to address performance concerns within these cloud environments. But what exactly is observability in this context? How is it different from, say, traditional monitoring?
That's a great point. Observability is really the ability to capture internal system information. We're talking metrics, logs, traces, in order to analyze and respond to it effectively. It's not just about knowing what is happening, like traditional monitoring might tell you. It's about understanding the why and the how behind system behavior. This allows you to debug and understand complex systems that you don't physically control, which is key in the cloud. Logs in the cloud are a good example. They capture comprehensive info about activities like sign-in attempts, config changes, traffic flows between cloud resources. AWS CloudTrail, for instance, provides an event history of your AWS account activity. Really useful stuff.
But what's crucial to understand here, I think, is that while these logs are incredibly helpful for troubleshooting what has happened, retrospective analysis, looking back in time, they aren't typically intended to provide real-time insights into what is happening right now. It's kind of like reviewing a security camera recording versus watching a live feed, right?
Exactly, but perfect analogy. And that's where real-time monitoring in the cloud truly differentiates itself. It actively analyzes live data and reports this information with little or no delay to services specifically intended to respond to changing conditions. AWS CloudWatch, for example, can detect anomalous behavior in your cloud environments, set alarms, and trigger real-time automated responses. Think scaling up resources to handle a traffic spike or initiating a fix for a failing service, often without any human intervention at all. For professionals working with hybrid and cloud environments, understanding cloud observability is a critical managerial issue. It's about designing, integrating, selecting communication solutions that are not just efficient, but also dynamically responsive and, ideally, self-healing. It's really exploring the cutting edge, the current and future impact of these data communication technologies.
Okay, so now that we've covered the foundation of collecting network data, essentially listening to its heartbeat and watching its every move, the next logical step is to actively manage that network traffic. After diligently gathering all that information on traffic patterns and network status, we need to monitor our network status on an ongoing basis. This process really involves two major intertwined factors, doesn't it?
It does.
Performance management, which is all about optimizing how the network runs, and fault management, which focuses on preventing and resolving issues. But to manage effectively, you first need a clear understanding of your starting point.
And that starting point is what we call a performance baseline. A baseline is basically a set of measurements that establishes a standard for comparison. It represents your network's typical, healthy operation under normal conditions. It's essentially your network's normal heartbeat, its healthy resting state.
Okay, so what exactly should we measure for this baseline? Is it just bandwidth? And what's
Yeah.
the danger if you don't have one?
No, it needs to be comprehensive. Way beyond just bandwidth. Think about daily network traffic patterns. Device availability, are things up or down? Interface statistics like in-out errors and utilization percentages on ports. Overall utilization percentages for links, error rates, and jitter, that variation in packet arrival time. And this data should ideally be collected over an extended period, maybe a 6-week cycle, to capture all those weekly and monthly variations, maybe seasonal peaks and troughs too. The danger of not having a baseline, you just don't know what normal looks like. Any issue, any slowdown, then becomes a complete guessing game. You can't tell if a new application is causing a problem or if it's just, normal network behavior for a Tuesday afternoon.
Yeah, I can see how that would be incredibly frustrating.
Yeah.
Just chasing ghosts. The value of these baselines must be immense then for troubleshooting and planning.
They truly are. They allow a network professional to compare future performance increases or decreases, whether caused by network changes, new applications, or unexpected events. Compare that against past performance. This comparison helps in quickly identifying anomalies and accurately measuring the impact of any changes or optimizations. The more data you gather while establishing a network's baseline, the more accurate your predictions about future network behavior and capacity needs will be. It's absolutely foundational to troubleshooting effectively.
But forecasting network traffic patterns isn't always easy, is it? Even with a good baseline, traffic is inherently dynamic.
You're absolutely right. It's challenging. You have normal variations throughout the day, the week, the month, even different seasons. Plus, there are unpredictable impacts from new applications, changes in user behavior, or unexpected network events. Think about a sudden viral video causing a massive spike in streaming traffic, or maybe a new software update deployment hitting everyone across an organization at once. These things can throw off even the best predictions if you're not watching closely.
This brings us to key performance indicators, KPIs, or traffic analysis. These are the vital metrics you'll track against your baseline. What are some of the most critical ones we should be watching?
Okay, well first, device availability and performance. Simply, is the router up? How efficiently is it processing data? Basic but essential. Then there are interface statistics. Detailed data on traffic flowing in and out of specific network ports, including packet counts and, importantly, error rates. Utilization is the percentage of a network link's or device's capacity that is currently being used. High utilization often signals potential bottlenecks ahead. The error rate tells you the number of corrupted bits or packets. A high rate often points to problems with cabling, maybe faulty devices or interference.
And we can't forget packet drops, right?
Mm-hmm.
Packets that simply fail to reach their destination due to congestion or hardware problems. Then there's jitter, which is the variation in packet delay at the receiver. High jitter disrupts that smooth, periodic arrival of data packets, severely impacting real-time applications like VoIP and video conferencing. It's like a stutter in a conversation, making it almost impossible to understand what's being said clearly.
And speaking of delay, latency is the actual delay between a sender transmitting information and the receiver decoding it. This is primarily a function of the signal's physical travel time and the processing time at any intermediate nodes, like routers. The speed of light imposes a minimum propagation time, meaning roughly an additional millisecond of round-trip delay for every 100 kilometers, or about 62 miles. You can't beat physics.
Right. This is where those Reddit discussions on latency reduction get really interesting, especially for gamers. Everyone wants to shave off milliseconds. But how much can you really do to fight the speed of light from your home network?
Yeah, it's a common quest. But for competitive online gaming, latency is predominantly dependent on physical distance to the game server and the efficiency of your internet service provider's routing path. While minor home network tweaks, like maybe changing your DNS servers to Cloudflare or Google, might feel like they reduce latency for initial website queries, they won't significantly speed up an established game connection that's already running. Significant improvements, say from 31 meters down to 29 meters, are often marginal at best and frankly imperceptible to most humans, even using a dedicated network interface card, an NIC, over an onboard one. That might have offered a tiny improvement under heavy system load years ago, but it's less impactful now. Adjusting the maximum transmission unit, the MTU, value in your router can help ensure packets fit better and prevent fragmentation for streaming, maybe. But its impact on gaming latency is often very limited. Ultimately, major latency reductions usually involve factors outside your immediate home control, like ISP routing optimizations or just being physically closer to the game servers. It all comes back to the fundamentals of telecommunications and data communications technology. You just can't defy physics easily.
Good reality check there.
Right, and contrasting with latency, we have throughput. Throughput is the actual rate at which information is successfully delivered per unit time. This is the how much data actually gets through. It's controlled by available bandwidth, the signal-to-noise ratio, hardware limitations. Sometimes people use it interchangeably with bandwidth, though they're technically different.
Okay.
And bandwidth itself is the maximum rate that information can be transferred over a network. That's the capacity of the pipe.
So it's the interplay of all these factors, latency, throughput, bandwidth, jitter, packet loss, coupled with user requirements and perceptions, that determines how fast or useful a network connection really feels.
Exactly.
For example, in TCP/IP, a large bandwidth delay product combined with small TCP window sizes can cause throughput to drop sharply with high latency. This can sometimes be fixed by increasing the TCP congestion window size or techniques like packet coalescing, TCP acceleration, or forward error correction, which you see often for high latency satellite links.
Right.
Understanding these metrics and their relationships is crucial for applying appropriate network troubleshooting techniques, a key skills outcome for any IT professional. Okay, now that we understand our network's baseline and the KPIs we need to watch, the next step is active bandwidth management. This isn't just a single trick. It's really a collection of strategic techniques designed to optimize the volume of traffic a network can support efficiently and effectively. It's a critical subset of overall performance management, and its core techniques include things like flow control, congestion control, and quality of service, or QoS. How do organizations even begin to tackle something this complex? Where do you start?
Well, it really starts with a strategic approach. Network observability leaders, like Kentic, outline a kind of life cycle that's incredibly valuable for business students to understand. First, you assess network requirements. You have to truly understand the bandwidth needs, the demands of different users, application-specific requirements. This involves regular audits, predictive modeling. Then, you implement traffic analysis using advanced monitoring tools, maybe like NetFlow, or specialized platforms to get granular visibility into bandwidth-intensive applications. This allows you to optimize traffic flow and ensure mission-critical applications get the priority they need.
Okay, so it's a cycle.
Yeah.
Understand, analyze, and then actively optimize. What about the physical infrastructure itself? Does that play a role in bandwidth management?
Oh, absolutely. That's where optimizing network infrastructure comes in. This means carefully selecting and configuring high-performance network hardware routers, switches, cables, investing in devices that support the latest applications, performing regular firmware software updates, implementing modular designs, maybe virtualization techniques like SD-WAN, and definitely redundancy for resilience and scalability. Then, crucially, you use specific bandwidth management techniques like flow control, congestion control, and QoS, which we'll dive into in more detail. And you simply cannot forget ensuring network security, because threats like distributed denial of service, DDoS attacks can severely degrade performance, making all your other optimization efforts pretty much moot.
Right, a DDoS can just flood the pipe. This sounds like a continuous effort, definitely not a one-and-done project.
Exactly right. It requires continual network monitoring and maintenance, proactively identifying and resolving issues, performing updates, maintaining comprehensive, up-to-date network documentation. That documentation part is key. And it demands network capacity planning, assessing current utilization, and predicting future needs based on business growth and tech trends. You have to ensure the network can handle growth without compromising performance. Finally, with the widespread adoption of cloud services, cloud networking optimization is vital. This involves ensuring reliable connectivity between on-premises and cloud environments, think AWS Direct Connect or Azure Express Route, monitoring cloud network and application performance, and implementing robust security measures like zero trust in those cloud environments. This entire strategic framework is vital for understanding the current and future impact and direction of data communication technologies. It really shapes how businesses thrive in today's hyper-connected world.
And here's where it gets really interesting, maybe even a bit futuristic. Artificial intelligence, AI, is rapidly becoming a game changer in bandwidth management and network optimization. It's offering significant strategic advantages for telecom and business networks. How exactly is AI transforming this space?
Yeah, AI's impact is profound, mainly because it addresses the sheer scale and complexity of modern networks that humans struggle with. AI can analyze massive volumes of network data in real time, identifying subtle patterns and anomalies that no human operator could ever hope to catch consistently. And this isn't just about spotting problems, it's about adaptive optimization. AI can dynamically adjust network configurations to optimize performance and resource allocation on the fly, reacting to changing traffic patterns and demands without needing manual intervention.
Wow. So AI acts like a super smart, always-on network administrator that can instantly reconfigure the network as needed.
Pretty much, yeah. And most crucially, perhaps, for proactive management. AI can predict potential network problems before they occur. This enables proactive maintenance and can actually prevent outages altogether. Think about it. AI intelligently routes and manages network traffic to prevent congestion, dynamically rerouting data as needed. It optimizes the allocation of network resources like bandwidth, processing power, storage, ensuring efficient utilization. AI algorithms analyze data to detect unusual patterns, signaling potential problems and preventing failures before they impact users. And it ensures high-quality service by prioritizing network traffic according to the specific requirements of various applications, which ties directly into QoS.
The economic impact of this must be absolutely staggering.
It is. Some projections estimate AI-powered network optimization could save the telecom industry something like $3 trillion by 2025. It's huge. Major players like AT&T and Vodafone are already actively implementing AI for network optimization. However, it's not without its challenges, of course. AI in telecom raises concerns about data privacy and security, given the massive data volumes involved. Potential bias in algorithms if the training data isn't perfect or complete. Compliance with evolving regulatory requirements and the security of the AI-powered systems themselves. These considerations are vital managerial issues when you're selecting and configuring network connections, services, security, and management for a robust and ethical network.
Okay, let's drill down into some of those specific bandwidth management techniques you mentioned, starting with flow control. If we think of our network as a series of roads, flow control is like a very smart traffic light on a local connection between two directly connected devices. What's its entire purpose? Why do we need it?
Its purpose is simple but absolutely critical: to prevent a sender from overwhelming a receiver with too much data too quickly. Imagine trying to have a conversation with someone who's just constantly interrupting you before you can process what they said.
Yeah, impossible.
That's kind of what happens if one device blasts data at another without any flow control. It can be implemented at various layers of the OSI model, commonly at the data link layer, but also sometimes within the network and transport layers.
Okay, and we have three common flow control methods mentioned.
Yeah.
The simplest is stop and wait. The sender transmits one frame and then literally waits for an explicit acknowledgement, an ACK, from the receiver before sending the next. Why is that so inefficient for modern high-speed networks? It sounds terribly slow.
It is incredibly inefficient, especially on links with any significant latency. The sender just sits idle for the entire round-trip time, even if the link itself is very fast. Imagine sending a single email, then waiting for a confirmation email saying, "Got it," before you're allowed to send the next one. Yeah, way too slow for today's data volumes. Then you have the go-back-end sliding window method. Here, the sender can transmit multiple frames before receiving an acknowledgement, using a window of allowed unacknowledged frames. But if any frame is lost or corrupted, the receiver discards all subsequent frames, even if they arrived okay, and the sender has to retransmit all frames starting from the lost one.
Ouch. So if frame number 3 is lost,
Yeah.
it has to resend 3, 4, and 5, even if 4 and 5 were actually received correctly the first time.
Exactly. It's better than stop and wait, but still pretty wasteful of bandwidth. The most advanced and generally most efficient method is the selective repeat sliding window method. It's similar to go back in using a window, but if an error occurs, the receiver actually buffers the correctly received frames that come after the lost one. The sender then only retransmits the specific frames that were lost or corrupted. This leads to much better link utilization, though it does require more complex buffering capabilities at the receiver. It's like asking someone to repeat only the specific sentence you missed in a conversation, rather than making them repeat everything since you last understood them. Much more efficient.
Okay, so if flow control is managing traffic at a single intersection, like between two devices,
Yeah.
then congestion control is more like managing traffic across an entire city, trying to prevent total gridlock. Its goal seems broader, to both prevent congestion before it occurs, which you called open-loop congestion control.
Right, the proactive approach.
And to remedy congestion, once it has already started, that's closed-loop congestion control. It's all about managing network resources to ensure smooth traffic flow, especially in shared environments like the internet.
Exactly. For open-loop techniques, those prevention strategies, you can configure various policies proactively. The retransmission policy defines how and when lost packets should be retransmitted to avoid adding more congestion during the recovery process. The window policy determines the size of that data window a sender is allowed to transmit before requiring acknowledgement, influencing how much data is in transit at any given time. Think of it as controlling how many cars are allowed onto a busy freeway entrance ramp at once.
Okay, makes sense. And what about managing the feedback loop itself? How does the network signal problems?
Well, then there's the acknowledgement policy, which specifies how acknowledgements, or ACKs, are handled to provide feedback on current network conditions. And the discarding policy, which dictates which packets to drop if congestion is imminent or already occurring. This often involves prioritizing certain types of traffic over others. Finally, the admission policy decides whether to even admit new connections or traffic flows into the network based on the current load and resource availability. It's kind of like a bouncer at a club. Turning people away when it's already full prevents overload.
Right, preventing overload before it starts. On the other hand, closed-loop techniques are the response strategies implemented when congestion has already occurred. How does the network actually realize it's congested in these cases?
Good question. One way is through implicit signaling. This is where the sender deduces congestion indirectly through observations like increased round-trip time, RTT, or seeing more packet loss than usual. It's like realizing there's a traffic jam ahead because your travel time suddenly doubled for no apparent reason. Then there's explicit signaling, where network devices like routers explicitly inform senders about congestion. They might use dedicated control messages or set specific bits within packet headers, like ECN explicit congestion notification in TCP.
I've heard of choke packets before. What exactly are those? It sounds pretty direct.
They are direct. A choke packet is a specific type of control packet sent back to the source by a congested router. It basically instructs the source device to reduce its sending rate immediately. Imagine a traffic controller directly radioing a specific car and telling it to slow down now. And back pressure is another technique where congestion at one node, say one router, propagates backward to the upstream nodes, effectively slowing down traffic flow throughout the entire path leading up to the bottleneck. It's like a traffic jam building backward from one clogged intersection to the previous ones along the route.
Okay, so we've talked about controlling individual flows and managing overall congestion. But what if some traffic is simply more important than other traffic? That's where quality of service, or QoS, assurance comes in. This is a group of techniques for adjusting the priority a network assigns to various types of transmissions. The goal is to manage network resources to ensure a certain level of performance for specific applications or data flows, especially the critical ones.
And what's fascinating here and really important from a business perspective is that different applications have vastly different needs. Delay-sensitive traffic like voice over IP, VoIP, video conferencing, or online gaming requires minimal latency and minimal jitter to function effectively. You simply can't have a business video call where the audio keeps cutting out, or a gamer experiencing lag during a critical moment in a competition. It ruins the experience. Conversely, loss-tolerant traffic, like maybe large file transfers or email, can handle some packet loss, but prioritizes high throughput for efficient data delivery. It doesn't matter if it takes a few extra seconds, as long as it gets there reliably. The business implication is clear. You need to ensure your critical VoIP calls don't drop just because someone in marketing is downloading a massive video file. You need priorities.
Makes sense. So to achieve this, we use techniques like traffic shaping, sometimes called packet shaping. What's the core idea behind shaping traffic?
Traffic shaping is an active mechanism that manages network traffic flow primarily by delaying certain packets, usually through buffering them temporarily. The goal is to meet predefined service level agreements, SLAs, or optimize overall network performance. Its main goals are to smooth out traffic bursts, delay less important traffic to let critical traffic through first, increase the priority of more important traffic, or limit the volume or momentary throughput rate of an interface. It's kind of like putting a speed bump in the road for less urgent traffic while giving priority lanes to emergency vehicles. Now, there was a controversial example back in 2007 involving Comcast. They allegedly used traffic shaping techniques to throttle or slow down peer-to-peer PDP traffic,
Yeah.
which sparked huge debates around network neutrality and who gets to control data flow on the internet. Still a hot topic today.
Yeah, definitely. So shaping gently slows things down, smooths things out. What if you need a more aggressive approach, where you simply cannot allow traffic above a certain threshold no matter what?
Right.
In contrast to shaping, traffic policing is a much more aggressive form of traffic management. While shaping attempts to buffer and smooth traffic, policing enforces a hard rate limit. It's like a strict rule. If traffic exceeds the configured rate, packets are typically just dropped or maybe remarked to a lower priority level. Imagine you have a data pipeline with a strict maximum capacity. Traffic shaping tries to make sure the flow is smooth up to that capacity. Policing acts like a bouncer at the door, simply turning away any excess traffic once that limit is hit. No exceptions. Use policing when strict adherence to a bandwidth limit is absolutely essential, perhaps to protect critical network resources from being overwhelmed by non-essential traffic floods.
Okay, shaping delays, policing drops. Then there's outright traffic prioritization. How do you actually decide what gets to go first? What are the criteria? You can prioritize traffic based on all sorts of characteristics. It's quite flexible. For instance, by the protocol being used, maybe prioritizing SIP for VoIP over HTTP for general web browsing, or by the IP address of a critical server, or maybe a specific executive's computer, giving their traffic preferential treatment. You can even prioritize by user group, giving higher priority to, say, the finance department's applications during month-end closing. At a more technical level, you can use the diffserv flag in an IP packet, specifically the DSCP value for IPv4 or the traffic class field for IPv6 right there in the Layer 3 header to mark packets with priority levels. And within a local network, you can use VLAN tags in a data link layer frame employing class of service or CoS values at Layer 2 for prioritization within a switched environment.
Okay, so just to clarify that, distserv is working at layer 3, typically across wider networks, maybe between routers, and CoS is more for local network prioritization, like within a building using switches and VLANs.
That's a great way to summarize it, yes. Diffserv, differentiated services, is a key technique addressing QoS issues by prioritizing traffic at Layer 3 of the OSI model using those specific fields in the IP packet header. The DSCP differentiated services code point is the field used in IPv4 headers, and traffic class is its equivalent in IPv6. Both indicate the priority and the desired per hop behavior for the packet as it travels. QoS, class of service, while sometimes used loosely synonymously with QoS, typically refers to traffic prioritization specifically at Layer 2, the data link layer, often using those VLAN tags. So yeah, think diffserv for prioritization across routers and the broader internet, and QoS more for prioritizing traffic within a single local network or switch fabric.
Got it. And what's absolutely critical for all this fancy prioritization to actually work then, it sounds like everyone needs to be on the same page.
Precisely. That's the key takeaway. For QoS benefits to be realized end-to-end, a network's connectivity devices, your routers, your switches, and potentially even the end clients, must support the same set of protocols and QoS policies. Otherwise, it's like building a priority lane on a highway, but the cars don't understand the signs or just ignore them. The priority marking gets lost or isn't honored. This directly relates to configuring network connections, services, security, and management for specific requirements. And it's a vital consideration when you're designing a professional network proposal to address a real business problem. You have to ensure QoS will work as intended.
All right, we've spent a lot of time on how to build, optimize, and prioritize our networks, make sure they perform at their peak. But, in the unpredictable world of data communications, proactive training and meticulous preparation are really the linchpin of a company's ability to respond to and adapt to both minor incidents and, major disasters and security breaches. Without a solid plan, even small disruptions can escalate incredibly rapidly.
Yeah, and it's crucial here to differentiate between an incident and a disaster. They aren't the same thing. An incident is typically a single limited event that might disrupt operations temporarily, like maybe a malware outbreak on one server or a minor power fluctuation affecting a single rack, or even just a misconfiguration on a switch by mistake. A disaster, on the other hand, is a much larger, more severe event. It causes significant disruption or loss across multiple systems or users, potentially impacting the entire business's continuity. Think of a data center fire, a widespread ransomware attack that cripples an entire organization, or a regional natural disaster like a hurricane or earthquake. Much bigger scale.
Right. So when an incident, large or small, occurs, you need to react with precision and have a clear roadmap. That's where an incident response plan, or IRP, comes in. This is a formal document, right? It defines the characteristics of an event that qualifies as a formal incident and outlines the specific step-by-step procedures that should be followed as a result. It's like a meticulously rehearsed blueprint for handling security events effectively and consistently.
Exactly. And formal incidents can be anything from physical break-ins, fires, weather emergencies, to sophisticated hacking attacks, the discovery of illegal content on company systems, widespread malware outbreaks, or even environmental disasters impacting a local area. To manage these effectively, organizations typically follow a 6-stage incident response lifecycle. It provides a structured approach to detect, respond to, and recover from cybersecurity incidents.
Okay, let's walk through that life cycle. The first stage is preparation. This happens before any incident occurs. What are the key activities here?
This is where you lay all the groundwork. It involves developing policies, procedures, acquiring the necessary tools. Key activities include actually creating that formal IRP, often starting with templates but customizing them to the specific organization's needs and risks. Establishing a dedicated computer incident response team, often called a CERT or CCERT, setting up clear communication channels and escalation procedures, who calls who when something bad happens. Implementing robust security monitoring systems like SIEMs, and procuring detection and analysis tools. And, as insights from companies like Atlassian emphasize, an effective incident response team needs diverse expertise. You need an incident commander to lead, DevOps teams to dig into root causes, operations teams for infrastructure knowledge, IT support, legal advisors for compliance, and crucially, an executive sponsor to provide leadership and resources. It's really a cross-functional team effort.
Okay, that's a lot of prep work. So once all that preparation is done, the next stage is detection and identification.
Yeah.
How do you actually spot an incident in the making?
Yeah, this is where the monitoring pays off. Here, the team actively detects and classifies potential security incidents. Assigning severity levels like critical, high, medium, low is key here to prioritize response. This involves continuously monitoring systems and networks for anomalies, collecting and analyzing security logs and alerts, like those from SIEM systems we mentioned, and triaging incidents based on predefined criteria. It's like a digital neighborhood watch, constantly scanning for anything out of place or suspicious. This directly relates back to identifying network architecture to facilitate troubleshooting techniques.
Okay, makes sense. Then comes containment. This sounds like putting on the digital emergency brakes fast.
That's a perfect way to put it. The immediate focus is on limiting the spread and the overall effect of an incident to prevent further damage. Stop the bleeding. This means implementing short-term and maybe long-term containment measures, like isolating affected systems and networks from the rest of the environment, blocking malicious traffic and access attempts at the firewall or endpoint, applying urgent security patches and updates if a vulnerability is being exploited, and meticulously, carefully collecting and preserving evidence for further analysis and potential legal action.
Following that, we have remediation, sometimes called eradication. This is where you not only stop the incident, but also completely clean up the mess.
Right. This phase identifies the root cause of the incident, how did they get in, and completely removes it from the environment. Activities might include removing malware and any compromised files or accounts, closing identified vulnerabilities and security gaps that allowed the incident in the first place, resetting compromised passwords, revoking compromised credentials or API keys, and potentially rebuilding affected systems from clean, verified backups to ensure no backdoors remain. It's a thorough digital cleanup.
The fifth stage is recovery. Okay, once everything's cleaned up, how do you get back to business as usual safely?
The goal here is simply to restore systems and operations to their normal, fully operational state. Core activities involve restoring data and configurations from those clean backups, thoroughly testing and validating the integrity and functionality of the restored systems. You have to be sure they work correctly. Monitoring vigilantly for any signs of reinfection or residual issues. Sometimes attackers leave things behind. And communicating the successful resolution to all relevant stakeholders, management, users, maybe even customers, depending on the incident. It's about building confidence that you are truly back to normal.
And finally, and this seems absolutely critical, is lessons learned. This post-incident phase must be paramount to avoid repeating the same mistakes.
Right. Absolutely, you nailed it. This post-incident activity ensures continuous improvement of the incident response process. It's often overlooked, but so important. It involves conducting a comprehensive post-incident review and analysis, sometimes called a post-mortem. What went well, what didn't? Identifying specific strengths and weaknesses in the response process, updating incident response plans and procedures based on the insights gained from the current incident, and maybe providing additional training or resources to the incident response team based on gaps identified. It helps refine your security strategy, which is a critical skills outcome for anyone in this field.
The importance of effective incident response just cannot be overstated. Beyond just fixing the immediate problem, what are the overarching business benefits of having a well-oiled IR process?
Yeah, a well-executed IRP is vital for mitigating all sorts of consequences: operational, legal, reputational. First, it minimizes damage. Quick and effective response significantly limits operational and financial impact, reducing downtime, data loss, and recovery costs. Second, it protects sensitive data, customer information, intellectual property, financial records from breaches, and unauthorized access, which helps maintain trust. Third, it maintains trust and reputation. Prompt and transparent communication, coupled with a well-executed response, demonstrates a commitment to security and customer protection. That's huge. And fourth, it ensures regulatory compliance with standards like GDPR, HIPAA, or PCI-DSS, helping businesses avoid hefty fines, penalties, and potential legal liability.
So with all these complex steps and the need for speed and coordination, what kind of tools are helping organizations streamline incident response today?
There's a whole ecosystem of tools. You have security information and event management, SIEM, systems for detecting threats and anomalies by aggregating and correlating logs from everywhere. Endpoint detection and response, EDR, tools help contain threats at the individual device level, laptops, servers. Forensic tools assist with deep dive evidence collection and analysis. Collaboration platforms are key for team coordination, especially when teams are distributed. And platforms like Atlassian's Jira Service Management can actually centralize alerts from various tools, host routine cooperation, and even automate certain response workflows, creating a single command center for incident management. And what's even more powerful now is the increasing role of AI in incident response.
AI again.
Yeah. AI constantly monitors network traffic and user behavior to identify and respond to potential security threats, often faster than humans can. Machine learning algorithms are highly effective at detecting anomalies, unusual events, new malware signatures, unauthorized network access, things that deviate from normal established behavior. And AI can even automate predetermined actions in response to detected threats, significantly reducing the time required to contain and resolve security breaches and minimize the impact. It's really about configuring network security and applying advanced troubleshooting techniques with a cutting-edge, intelligent ally.
Now, when an incident involves a security breach or maybe even illegal activity, any data collected might need to be presented as evidence in a court of law. This means you need extremely careful and legally compliant data collection methods. This isn't just about technical recovery anymore. It's about legal accountability and protecting your organization.
Absolutely. That's where the role of first responders becomes critical. These are individuals who should have specialized training, maybe certifications in digital forensics. They are prepared to handle evidence in such a way as to preserve its admissibility in court. Their actions from the very outset are absolutely crucial. You can't mess this up. Think of it exactly like a crime scene investigator carefully bagging and tagging physical evidence at a crime scene. Digital evidence requires the same meticulous attention to detail to ensure it's not contaminated or altered, which would make it useless in court.
Okay, so until a dedicated, trained incident response or forensics team can take over, what are the absolutely critical steps that maybe an initial IT responder needs to take to safeguard information and ensure its legal integrity?
Great question. First, secure the area physically. Prevent contamination or unauthorized access to any affected devices or locations. Lock the door, put up tape, whatever it takes. Then document the scene meticulously. Record all observations, conditions, initial findings. Take photos or videos if possible. Note the time, who's present. You also need to monitor evidence and data collection very carefully to ensure it's consistent and follows established protocols. Don't just randomly start copying files. Critically, you must protect the chain of custody. This is paramount. Maintain a clear, unbroken, documented record of who has handled the evidence, when they handled it, and for what purpose, from the moment it's collected until it might be presented in court. Every handoff must be logged.
Wow, Okay, chain of custody is key. And finally, even just moving this data needs careful documentation.
Yes, absolutely. You must monitor transport to ensure the secure and documented transportation of any data or equipment containing potential evidence. How was it moved? Who moved it? And throughout this entire initial process, you create a report documenting all actions taken, observations made, and individuals involved in that initial response. Every single step is about maintaining integrity and accountability for that potential evidence.
Okay, so while incident response deals with specific, often localized events, disaster recovery planning is really about preparing for that worst-case scenario. The big one, the overarching goal here is business continuity, BC, right? Which is the ability of a company to continue doing business with the least amount of interruption possible during and after a disaster or major disruption.
That's the goal, yeah. And a business continuity plan, or BCP, is the comprehensive document outlining the resources and protocols a business will use to continue providing service to its customers with little or no disruption during a disaster. It covers everything: people, processes, technology. The disaster recovery, or DR plan, is a critical part of that broader BCP. It specifically details the processes and procedures for restoring critical IT functionality and data after an outage that affects more than just a single system or a limited group of users. Think region-wide power outage, major natural disaster, catastrophic cyber attack. It's about building networks to facilitate troubleshooting techniques even under duress, and developing a physical design focused on resilience.
So when designing a robust network DR plan, what are the absolute non-negotiables? What are the key areas businesses absolutely need to think about?
There are several critical areas you just can't ignore. First, infrastructure resilience. This means ensuring you have current and accurate network diagrams reflecting any recent changes. You need to know what you have. And critically, conducting regular risk assessments of both physical and logical network elements, including your perimeter security, to identify those dangerous single points of failure. Where can one failure take down everything? For local area networks, this means built-in redundancy in the structure, safe cabling practices, secure housing for routers and switches, and maintaining an inventory of spare LAN components. For wide area networks, you need to consider how redundant your links are. What happens if your primary circuit fails? What recourse do you have if your carriers experience a major outage themselves?
Right, those external dependencies are huge. And what about the power backbone and security?
Exactly. You need to assess the security and survivability of your internet service providers, ISPs, and understand their recovery plans. Don't assume they'll always be there. If you use VoIP, what DR support does your PBX vendor provide? Do they have failover options? Crucially, emergency power systems are essential. Beyond just commercial power, do you have UPS systems, generators? And critically, are they properly sized to run your critical systems VoIP, LAN, WAN for the required duration? And perimeter security is vital. Robust defenses against malware, ransomware, phishing, DDoS attacks are part of DR too. This also includes having emergency resources ready to recover network integrity, using encryption properly, and keeping firewall rules regularly updated and backed up. Finally, don't forget backups of your network software itself, operating systems, configurations, and having wireless network recovery assets, and understanding the DR services available from your wireless carriers. These are all fundamental components of designing a logical network and developing an appropriate security strategy to mitigate risks.
Wow, that is a comprehensive list. It sounds like an enormous undertaking to put a solid DR plan together. What are the key strategies and maybe some potential challenges in this process?
It definitely requires careful planning and ongoing effort. You start by running risk assessments of all your network assets. It helps to consider relevant industry DR standards for guidance, things like NIST SP 834 for federal systems, or the international standard ISO 2T3001 for business continuity management systems. You need to meticulously document detailed policies and procedures for every DR activity, who does what, when, how. You also need to assess your primary and, importantly, alternate suppliers, ISPs, wireless carriers, cloud vendors. Do they have redundancy? What are their SLAs? Evaluating diversely routed network configurations for both local and wide area networks is crucial. Don't have all your fiber running down the same street. Securing appropriate physical space for network devices and ensuring proper HVAC systems are in place is also part of it.
And I imagine all this planning means absolutely nothing if you don't actually test it, right?
Precisely. That's probably the most common failure point. Most importantly, you must test DR plans periodically, annually, semi-annually, to ensure backup resources actually work properly and the procedures are effective and people know them. Tabletop exercises, full failover tests, you review and contain DR resources regularly, and critically, you train network teams and other relevant staff in the DR procedures. People need to know their roles when disaster strikes. This comprehensive approach isn't just about ticking a compliance box, it's about ensuring genuine network resilience, protecting your infrastructure and assets, minimizing downtime, and ultimately safeguarding the entire business's ability to operate through a crisis. It empowers you to address business problems with a professional network proposal that includes resilience, and it's a vital part of preparing for those industry-standard network certification exams, which heavily emphasize DR concepts.
Okay, part of planning for the worst is having somewhere else to go, right? Alternate sites. Disaster recovery contingencies are these predefined alternate locations or setups a business can leverage to restore operations after a disaster. And these are categorized based on that very real trade-off between implementation expenses and the time it takes to recover services.
Exactly. These categories clearly illustrate that cost-benefit analysis. A cold site is the most basic and usually the least expensive option. It's essentially just a facility with minimal infrastructure, maybe just space, power, and basic connectivity, but no pre-installed computer equipment. Recovery time here is the longest, potentially days or weeks, as all the equipment must be procured, shipped, installed, and configured from scratch.
Okay.
You're basically building a new data center on the fly. This might make sense for businesses that can tolerate significant downtime, but not for many.
Okay, so that's cold. Then you have a warm site. What's the step up there? How is it different?
A warm site is a mid-range option. It includes essential hardware and infrastructure servers. Networking gear might already be racked and powered, but it's not fully configured with the latest data or all applications. Recovery time is moderate, maybe hours to a day or two, requiring data restoration from backups and final configuration steps. It's like having the basic skeleton of a new office ready, but you still need to move in your latest files and set up your specific systems to be fully operational.
Okay, warmer, faster.
Yeah.
And the gold standard, the quickest recovery option. That must be the hot site.
That would be the hot site, yes. This is the most comprehensive and consequently the most expensive option. It's a fully equipped, configured, and often synchronized facility that mirrors the primary production site in near real time. It's ready for immediate switchover with minimal downtime, potentially just minutes. For mission-critical operations where every minute of downtime costs a fortune, think financial trading floors, emergency services, a hot site is often essential. Choosing between these directly contributes to your logical and physical network design based on business requirements.
And increasingly, we're seeing cloud sites, often referred to as zero disaster recovery, as a service. This leverages cloud infrastructure for disaster recovery, offering significant advantages in scalability, flexibility, and often cost-effectiveness compared to maintaining dedicated physical sites.
True, Duras is becoming very popular, but here's a crucial caution for anyone planning for Duras, especially students thinking about future implementations. You must consider the organization's cloud connectivity needs during a widespread disaster. Some types of major disasters, like a regional power grid failure, a major internet backbone cut, a massive denial of service attack affecting cloud providers, might prevent access to the cloud at all, at least for a critical period.
Good point.
This necessitates a diversified approach and underlines the importance of a robust overall physical design. You can't necessarily put all your recovery eggs in one, albeit highly advanced cloud basket without considering connectivity resilience.
All right, let's talk about something fundamental. Keeping everything powered up. Power management is such a critical part of network management, focusing on ensuring a stable and continuous power supply. Accounting for outages and fluctuations is paramount because, as you said earlier, even small power surges or inconsistencies can cause serious damage to sensitive computer equipment and be a really frustrating source of intermittent network problems. What are some of those common power flaws that can literally fry your expensive electronics?
Yeah, clean, stable power is non-negotiable. There are several common power flaws that can damage equipment. A surge is that sudden, brief increase in voltage above the normal level. Think lightning strikes nearby or major fluctuations on the utility grid. Noise refers to electromagnetic interference, EMI, or radio frequency interference, RFI, on the power line, which can corrupt data or cause weird device malfunctions. A brownout is a prolonged drop in voltage below the normal level. This often causes electronic components to operate erratically or even fail over time. Things might just act weirdly.
Yeah.
And of course, a blackout is a complete and total loss of power. Everything goes dark.
Okay, scary stuff. So, to protect against these, we have several mechanisms. A surge protector is a common device. Most people have these. Designed to protect electronics by diverting excess voltage. The PDUs, power distribution units. How are they different from just a power strip?
A PDU is more robust. It provides multiple electrical outlets specifically designed to distribute power efficiently to equipment within a server rack. PDUs often include better surge protection than consumer strips, and many offer advanced monitoring capabilities like measuring power draw per outlet remotely. But the most critical component for ensuring power remains available and clean and problem-free is the UPS, the uninterruptible power supply.
Right. Everyone probably has a small UPS at home for their PC, maybe their router.
Yeah.
But what are we talking about in a data center or critical business context? How do they work there?
A UPS provides temporary power from its internal batteries when the primary power source, the utility power, fails or fluctuates outside acceptable ranges. This allows connected equipment either to shut down gracefully, preventing data corruption, or to continue operating during short outages, maybe until a generator kicks in. UPS systems come in various capacities, measured in VA or watts, and different types, offering different levels of protection and runtime. Generally, though, there are two main categories. The standby, or offline UPS, is the most common and least expensive type, often used for desktops. It switches to battery power only when a significant power problem, like a blackout or severe brownout, is detected. There is a brief, typically a few milliseconds, switchover time.
Okay, so it's like a backup generator that kicks in really fast. And what about the more robust always-on option?
That would be the online UPS. This type provides continuous high-quality power to devices by constantly converting incoming AC power to DC to charge its battery, and then converting that DC power back to perfectly clean AC to power the connected devices. So the devices are always running off the battery power, which is constantly being recharged from the utility. This offers zero transfer time during an outage and provides the highest level of power conditioning, filtering out noise, regulating voltage constantly, making it ideal for critical systems like hospital equipment, financial transaction systems, core network routers, where even a millisecond of interruption or dirty power is unacceptable. When selecting a UPS, you really need to consider the total amount of power needed, at the wattage of everything, the required time you need to keep devices running during an outage, just for shutdown or longer, its line conditioning capabilities, how clean is the power, and naturally the cost. It's a balancing act.
All right, our final line of defense against data loss, or system failure. Robust backup systems. A backup is simply a copy of data that can be used to restore information in case of loss, corruption, or complete system failure, like from ransomware or hardware crash. Backups seem absolutely fundamental for recovery, ensuring business continuity, and mitigating the impact of all sorts of incidents. Regular audit reports can even identify problems or deficiencies in backup systems based on compliance standards, right?
Absolutely. Backups are non-negotiable. Designing and configuring an effective backup system requires careful planning, though. You need to determine what data is critical. You probably can't back up everything. How often it needs to be backed up, recovery point objective, and where the backups will be stored securely. There are three primary types of data backup strategies. A full backup copies all selected data every single time the backup job runs. It's the simplest method for restoration. You only need the latest full backup set. Easy peasy. But it takes the longest time to complete and requires the most storage space, especially over time. You'd use this for crucial systems where simplicity of restoration is the absolute top priority, even if it's resource intensive.
Okay, so a full backup is easy to restore but slow and big to create. What about more efficient options for, say, daily backups?
Right. Next is an incremental backup. This copies only the data that has changed since the last backup, whether that last backup was a full or another incremental. This is typically the fastest type of backup to perform each day and uses the least amount of storage for each individual backup job. Very efficient. However, restoration is the slowest and most complex. You need the last full backup plus all the subsequent incremental backups in the correct sequence up to the point you want to restore.
Ooh, complex.
Yeah, if one incremental in the chain is bad, you might be in trouble. Imagine restoring a document by applying the original version, then every single tiny change you made to it, one by one, in perfect chronological order. It works, but it's tricky.
Okay, tricky restore. And finally, the differential backup. How does that fit into the picture? What's the trade-off there?
A differential backup copies only the data that has changed since the last full backup. So each differential backup grows larger over time until the next full backup. It's faster to perform than a full backup, since it only copies changes since the last full, and it's generally much faster and simpler to restore than an incremental backup. You only need the last full backup and the latest differential backup, just 2 sets.
Much simpler restore.
Yeah. This offers a really good balance between backup speed storage efficiency and restoration simplicity speed. You'd often choose this if you need frequent backups, but also want a relatively quick and reliable restore process without managing long chains of incrementals.
Okay, full, incremental, differential. Got it. Now, to ensure truly robust data resilience, we have the 3-2-1-1 rule. I hear this mentioned a lot as a best practice strategy. Could you break down what each number means and why it's so vital, especially that last one?
Sure. This rule is a fantastic guideline, a cornerstone of modern data protection strategy. The first 3 means maintain at least 3 copies of your critical data. That's your primary production data plus at least 2 backup copies. The 2 means store these backups on at least 2 different types of media. For example, 1 copy on local disk arrays and another copy on cloud storage, or maybe 1 on disk and 1 on tape. This protects against a single type of media failure or issue. The first one dictates keeping at least 1 copy offsite, geographically separated from your primary data center. This provides protection against regional disasters like fires, floods, earthquakes that could destroy your main site and local backups.
Okay, 3 copies, 2 media types, 1 offsite. Makes sense. And that final, crucial one for the modern threat landscape, what does that represent?
That additional 1 is increasingly critical today, especially with the rise of ransomware. Ensure at least 1 copy of your backup is immutable or air-gapped. Immutable means the backup data, once written, cannot be altered or deleted for a set period. Ransomware can't encrypt it. Air-gapped means the backup is physically isolated from the network. Think offline tapes stored securely, or logically air-gapped cloud storage that can't be accessed directly from the production network. This provides absolutely critical protection against ransomware or malicious insider threats that could otherwise try to find and corrupt all your online or network-connected backups. It's the ultimate break glass in case of emergency data copy. All these backup strategies, the frequency, the type, the location, they're all driven by 2 key metrics that affect your contingency plan options. The RTO, or recovery time objective, the maximum acceptable downtime for a system or service after an outage, how quickly do you need to be back up, and the RPO, or recovery point objective, the maximum acceptable amount of data loss a business can tolerate, measured in time. How much data, maybe an hour's worth, a day's worth, are you willing to lose from the point of failure? Understanding RTO and RPO and applying these backup strategies are critical skills for formulating risk assessments and developing appropriate security strategies. And this directly contributes to your preparation for industry-standard network certification exams, which definitely emphasize practical backup and recovery knowledge. Hashtag outro.
Wow, okay, what a deep dive that was, seriously. We've journeyed through the intricate dance of network packets, the unseen threats to network health. We explored the vital role of monitoring tools like SNMP and NetFlow and truly listening to our networks. And we've delved into the absolutely indispensable strategies for incident response, disaster recovery, power management. We even touched on the transformative power of AI in keeping our networks resilient, secure, and dynamically optimized. It's a lot to cover.
It is. And remember, we started by considering the impact of network failures from just a small gaming lag all the way to a catastrophic system collapse. Now, hopefully you understand that ensuring seamless connectivity isn't just about avoiding a gaming hiccup. It's truly about safeguarding critical business operations, protecting sensitive data, maintaining customer trust, and ensuring the very continuity of an organization. The robust performance and swift recovery of a network. They are the silent yet absolutely essential guardians of our digital world.
So true. Well said. If you found value in this deep dive into network performance and recovery, and I hope you did, please show your support by liking this episode, subscribing to the deep dive for more expert insights, and sharing it with your peers, maybe others in your classes. And don't forget, the description below has even more resources to help you continue building your expertise and positioning you for a bright future in your chosen career path.
Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.